Introductory neuroscience and neuroinstrumentation, axonology, neuronal biophysics, part 2. Okay. So we were talking about passive spread or electrotonic spread of potentials across dendrites, across axons, and this depends on something called the characteristic length or lambda. So consider the spread of electrotonic potential under steady state conditions. Okay. In standard cable theory, this equation defines it, where V is the voltage, then you have a term for membrane resistance, you have a term for internal resistance, and this is d squared V by dx squared is its spread over the length of the axon, the spread of the voltage or the length of the axon. So the steady state solution for this equation in an infinite cable for positive values of x gives V is equal to V naught e to the minus x by lambda. And here this is very straightforward to derive from cable theory, and here this term lambda is defined, it's defined as the square root of Rm divided by Ri. So resistance of the membrane, neuronal membrane, divided by internal resistance of the neuron, and V0 is the value of V at x equals 0. Okay. So when x equals 1, the ratio of V to V naught is e to the minus 1 or 1 by e or 0.37. Okay. So it reaches 0.37 of its original value at where x is equal to 1. So therefore lambda is a critical parameter defining the length over which the electrotonic potential decays to a value of 0.37 from the original value at the site of input. So this is referred to as lambda, it's also referred to as characteristic length, it's referred to as space length, or it's referred to as the length constant of the cable. Okay. So the higher the specific membrane resistance, capital R by M, leads to a higher value of Rm for the segment, that is the resistance of a patch of membrane. So therefore the value of lambda is bigger, and so the electrotonic potential spreads more. So the specific membrane resistance, capital Rm, is important variable in determining the spread of activity, this passive electrical activity in a neuron. So length and space constant and membrane resistance. So consider axon, 3 axons with 3 different values of lambda. Okay, this is where lambda of the first, this curve, this is the second, this curve, and this is the third, this curve. So the potential profiles for all these different values are on top over here, and the dotted lines represent the location of lambda on each of these processes. The physical distance is shown in red. So in the first case, because of the properties, it's only so much. In the second case, it's much more, and in the third case, it's even more. Okay. So Rm, some numbers. So Rm can vary in values from less than 1k ohm per square centimeter to more than 100,000 ohms per square centimeter in different neurons and different parts of a neuron. So note that lambda varies with the square root of Rm. So a 100-fold difference in Rm translates to only a 10-fold difference in lambda. Conversely, a higher value of specific internal resistance, Ri, so the higher the internal resistance, lowercase Ri, for that segment, the smaller the lambda and the less the spread of the potential through the segment. Okay, because the resistance prevents the electrical current from spreading. So the value of capital Ri is approximately in the range of 50 to 100 ohm centimeter in muscle cells and squid axon. In mammalian axons, in mammalian neurons, it's much higher, about 200 ohm centimeter. So this kind of limited range suggests that Ri is less important than Rm in controlling the passive current spread in a neuron, i.e. the internal resistance of an axon is not so important as the membrane resistance of the axon as far as the passive spread or electrotonic spread of electrical activity in the neuron. Furthermore, it's a square root relationship, so it further reduces the sensitivity of lambda to Ri. Okay? However, there are some caveats. So, in the cytoplasm, you have membranous and filamentous organelles, tubules, various things, mitochondria, endoplasmic reticulum, which we looked at in the microscopic anatomy of the central nervous system. All these may change the effective Ri. And also, the relative significance of Ri and Rm depends on the length of the given processes and how branched it is, and so on and so forth. So, the space constant also depends on the diameter of the process, besides the resistance which we considered before. So, thus from the relationships of Rm and capital Rm, Ri and capital Ri discussed in the previous slides, you can lambda is equal to square root of Rm by Ri, and that reduces to square root of the specific membrane resistance, specific internal resistance, and this d by 4 is the a term for the cross-sectional area. So, neuronal processes vary very widely in diameter. The thinnest processes are the distal branches of dendrites and the necks of dendritic spines. These have diameters of greater or equal to 0.1 mu. Note again that the relationship of lambda is to the square root, so a tenfold difference in diameter increases lambda by only 3 times. Okay. So, here we have the relationship of lambda to diameter. So, again you have 3 different axons with 3 different diameters, 1 mu, 4 mu and 16 mu, and you see the potential profile. So, lambda in the first one is over here, in the second one is here, and the third one is here, because it spreads much further because the cross-sectional area is much more. So, the to double lambda, the diameter must be quadrupled. Okay. So, the real length of a giant axon is several centimeters. So, to relate this real length to the characteristic length or lambda, we define electrotonic length or capital L of a cylindrical neurite as its physical length divided by its space constant. So, thus, if x is 30 millimeters, then L would be, that is the electrotonic length, 30 divided by 4.5 is equal to 7. So, the electrotonic potential decays to a small percentage of the origin value by 3 characteristic lengths. So, this has implications when you are stimulating a nerve. So, you can stimulate a nerve, and for whatever reason, experimental conditions, it goes down. You can move by 3 characteristic lengths, and then you have a brand new zone to stimulate, and the previous area does not affect the new stimulatory site. But these were axons, what we discussed so far. If you look at dendrites, they have lengths that are very much shorter in size than axonal lengths and characteristic lengths. So, therefore, in dendrites, what's important is the branching patterns, which modulate the extent of potential spread. So, action potentials overcome the attenuation of passively spreading potentials that occur over axon length. But this occurs to long axons, not to short axons and their collaterals. Okay. So, putting all this together, we have combined analog and digital signaling in neurons. So, you have the pyramidal cells over here on the right, a couple of them, and you have their extensive dendritic branches, and you'd have from the base of these cells axons leading on to other cells, one over here, and there's one behind, actually 3 of them over there. Okay. So, you have excitatory synaptic sites on the soma, and they get inputs from different cells, different networks, and depending on the amount of excitation, the amount of inhibition, they modify the analog signals. The analog signals reach a threshold. Once it reaches a threshold, you have action potentials which are kind of digital, all or nothing, and coded by frequency. So, these mechanisms are seen have actually been found in pyramidal cells. So, again, So you think of an analog computer over here, analog computation occurring in the dendritic branches, and this modulates action potentials coming out from the neurons, which is digital. So a single cell is a combined analog and a digital supercomputer. Okay. So fast signals. So how does electrotronic properties affect the spread of fast signals? So many neuronal signals change rapidly. So in mammals you have fast action potentials that last from 1 to 5 milliseconds, and fast synaptic potentials that last from 5 to 30 milliseconds. So rapid signal spread depends not only on all these factors discussed so far, but also on the membrane capacitance, because when there is a rapid change, capacitive effects come into play. And of course, just remind you, the capacitance is due to the lipid part or the lipid moiety of the cell membrane. Okay. And classically, we put the value of specific membrane capacitance C subscript m as 1 microfarad per centimeter square. Okay. So continuing with electrotronic properties and spread of fast signals. So here you have the equivalent circuit of a neural process. The membrane capacitance is in parallel with the ohmic components of the membrane condenser, the electromotive force and the driving potential. And neglecting the resting membrane potential, what we do is we inject current into a cell body. So the time course of the spread of current is described by two currents. One is the capacitive current, the part which discharges and recharges the membrane, and the resistive current, plus of course the input current which you are giving the pulse. So this would describe it, the capacitance. Then you have a resting membrane potential which changes, then you have a membrane potential, and then you have the resistance, and that is equal to the current pulse. So if we rearrange this and we substitute Rc is equal to tau, which is the time constant of the membrane, we get this, we are rearranging, we get this, and the solution for this equation for response to a step current change in potential is given by this equation, where t is equal to tau by time. When the pulse is terminated, the decay of the initial potential to rest is given by this equation. So it comes back to baseline, and again you see E and e to the power of minus t. Okay. So what actually happens? So you have an on transient and then you have an off transient. Okay, this is how it looks. You have a step current coming in here, and it takes some time for the membrane capacitant to discharge, recharge, to reach that thing. And when you switch it off, this is a square pulse, it again decays back to normal. So the on and off transient shown in the time required for the voltage change across the membrane to reach 1 by eth of its final value, which is 0.37. So this is similar to the way the length constant defines the spread of voltage over distance. Okay. So the equivalent circuit of a single isolated compartment responds to an injected step current by charging and discharging along a time course determined by the time constant tau. Okay. And for this figure, V is the steady state voltage, Im is the injected current applied to the membrane, just electrical square pulse on top of the axon. I subscript C is the current through the capacitance, I subscript I is the current through the ionic leak conductance, and tau is the membrane time constant. So consider a two compartment model. Okay. So you have two compartments, there is one compartment here and there is one compartment here. Okay, this is compartment A and this is compartment B. So in compartment A you have its equivalent circuit, you have the capacitive term and you have the resistive and the EMF term, and likewise with B. Okay. So this very simple two compartment model can be applied to the generation and spread of any arbitrary transient signal. So consider the simplest case. So this is compartment A and you inject current, positive charge here, and this flows outward across the membrane, partially opposing the negative charge on the inside of the lipid membrane. This negative charge is responsible for the resting membrane potential, and thereby it depolarizes the membrane capacitance at this site. Okay. At the same time, the charge begins to flow as current across the membrane through the resistance of the ionic membrane channels that are open in this site, across the membrane. And the proportion of charge divided between CEM and Ri determines the rate of charge of the membrane, that is the membrane constant. So the electrotronic current which spreads from one compartment to another is also called the local current. Okay. So in unmyelinated axons, if you remember, some axons have myelin insulating them, some of them are unmyelinated. In unmyelinated axon, the local current spreading through the internal resistance allows the propagation to the next compartment. So each of these cable properties is relevant in specific ways. So one, for brief signals such as an action potential, Cm, the capacitance, is critical in controlling the rate of change of membrane potential. For long processes such as axon, the internal resistance is important because it opposes the electrotonic current flow. Okay. So continuing, the effect of Rm, the membrane resistance, it decreases with increased membrane area because of parallel current paths. This is greater in thinner axons which have a shorter lambda. The specific resistance, capital Rm, can vary widely. So if it's high, then the current is forced to spread along the membrane, increasing lambda and spread. However, at the same time, tau is also increased, because if you remember, tau is equal to R into C, thus slowing the response of the neighboring compartment to this change. So consider what happens when you increase the diameter of an axon. It lowers, so here it's 1 mu, 4 mu and 16 mu. So it lowers the effective internal resistance, thereby it increases the space constant lambda, but without an effect on the time constant tau. Okay. So these are the effects. Cable properties are very important. They have very distinct effects on local current and electrotonic spread of current in the dendritic trees. So the question is, how do you make it conduct faster? Because once you have large brains, large brains compared to invertebrates, so we need to control large bodies, and that requires communications over long distances. Even though it feels very fast for us, thought and stuff, the maximum speeds of axonal conduction are only about 100 to 120 meters per second in humans, and much slower in lower forms. So there is this problem in evolution. How do you make axons conduct faster? So one way to increase axonal conduction is to increase the diameter. But there's a limit. You can't have the squid giant axon is probably the axon which we know with the maximum diameter. You cannot increase axons diameters indefinitely, because larger diameters means fewer axons within a given space, and fewer axons means less cognitive processing. So coming back to myelin, so one way is to increase the rate of conduction is to make the kinetics of impulse mechanism faster. So if you remember, we talked about myelin. So now we'll talk about the biophysics. So action potential in mammalian nerves are very fast. So with the wrapping of these cell membrane from the oligodendrocytes and the Schwann cells, more resistances are added in series with the membrane resistances. More capacitances are in series with the membrane capacitance. Remember, capacitances add as reciprocals. And this kind of insulates and forces faster conduction. We'll get to it in just a bit. So just to remind you, this myelin layers are provided by the Schwann cells in the peripheral nervous system and oligodendrocytes in the central nervous system. They wrap their cell membranes around an axon. And because of this, they are the fastest. Myelinated axons are the fastest in the central nervous system. So myelinated axons are not myelinated across the entire length. If you remember, we have nodes of Ranvier. They are interrupted. So here you have a cross section of an axon with the myelin layers and the Schwann cell over there, and here you have the longitudinal section, and here you see the node in between. So the density of sodium channels in the node is very high, about 10,000. It's much lower in the internodal regions, and internode is approximately 300 mu to 2000 mu. This difference in density means that most of the potential action happens at the nodes, not so much in the internodes. So the impulse literally jumps from one node to another, and it's called saltatory conduction or leaping conduction. So this makes it much faster, okay? And myelinated axons, one way to think of it is they resemble passive cables with active booster stations, okay? And Hirsch in 1939 found an empirical law that states that the rate of propagation of an impulse along a myelinated axon per second is 6 times the diameter of the axon in mu. So the largest neurons in the central nervous system are approximately 20 mu in diameter, and their conduction velocity is 120 meters per second. Thin myelinated axons are approximately 1 mu in diameter, and their conduction velocity is only 5 to 10 meters per second. So meters per second, very, very slow compared to transmission of electricity or light, very, very slow. Okay. So some more thoughts about myelination. So because of this saltatory conduction, the impulse, the length of the impulse, it may extend over a considerable length across the axon. So for example, in a 20 mu diameter axon conducting at 120 meters a second, at any given time, an impulse of 1 millisecond, this is a typical action potential, it extends over 120 millimeter length of axons, which includes more than 100 nodes of Ranvier. So one action potential, even though it comes up like this and goes down, it extends over 100 nodes of Ranvier. So this impulse is generated simultaneously by many nodes. The local currents activate adjacent nodes. So for axons of equal cross-sectional area, if you have myelination, impulse conduction increases 100-fold. But however, if the axon is less than 1 mu in diameter and all other factors are equal, there's an advantage for the axon to be unmyelinated. Okay, so with all these facts, how does current spread in a dendritic tree? Okay, so the dendritic tree constitutes conductance, loads, and activity, and these are the different kinds of dendritic trees. What have you? It's literally like the different trees in a forest. So the spread of activity from one site is determined by the impedance match or mismatch between that site and neighboring site. This is electrical theory. Like consider your speakers. Your speakers have a particular impedance. Now, if you use the wrong impedance, the output will be distorted or less. So this on the below is actually a compartment model of a Purkinje cell in the cerebellum, I think by DeSchuetter's group, and the soma is just a round sphere. We're not really interested in the soma. The action is over here in the dendritic branches, and if you notice, they have different diameters. Okay, and as you go to the periphery, they become thinner and thinner. And all this is electrical compartment modeling. This is not real. This is a model. Okay, but you can see how detailed it can get. Okay, so you have to get this concept of this equivalent cylinder. So again, all this stems from the work of Wilfred Rahl and Segev more recently. So rules governing impedance have been worked out in a particular case where the sum of the daughter branches raised to 3 by 2, it's 1.5 power, is equal to that of the parent branch. So here the system of branches is an equivalent cylinder resembling a single continuous cable. Okay, so this is the actual cell. You're making into compartments. You're putting, and you're assigning various C and R terms to each compartment. And finally, you get an equivalent cylinder resembling a single continuous cable. Okay. So when you have such a model, it's a starting point in analyzing both synaptic integration and equivalent dendrites. So integration of synaptic potentials in passive dendrites is nonlinear because different synapses have conductances, so they interact. So the rules for understanding electronic spread and electrotonic spread in dendrites are the basis for understanding the contribution of active properties of dendrites. Okay, so one thing to be borne in mind is that dendrites also have active conductances. So that adds another layer of complexity when you're modeling. And if you want to do realistic modeling, you have to assign and put in all these terms. Whatever we get from experimental physiology has to be added. and then only your model will replicate or kind of replicate what's happening in the real situation. So thank you. And further readings, if you're interested in this stuff, I strongly recommend you to check out Wilfred Rall and Rinzel, this is like Hodgkin and actually Rall and Rinzel for cable theory. Go on PubMed, put in Wilfred Rall, and you will get a lot of his original papers. And for those of you who like books, I strongly recommend Methods of Neuronal Modeling, From Ions to Networks by Christoph Koch and Idan Segev. So this is available from MIT Press, and I think you have copies of it available on the internet. So thank you very much. This has been a slightly complex session, and but you need to know all this to realistically model neurons, and that is possible. Thank you.